Hey guys, so classmate asked, can you go over question 2 for AP Statistics from the 2009 FRQ, specifically Form B for that year? Now these questions are available for free from College Board and are a great way to actually review for any AP tests you may take. And while this 2009 question is old and may be in a format that no longer aligns with the current version of the exam, these questions are still great ways to review and practice your skills in subjects like statistics. Now, if we first look at this question, we may notice how wordy and long it is, and so we may be tempted to just skip the entire introductory statement and head straight to the meat of the problem. But I would like to propose for us to actually pay attention to what this introductory paragraph is talking about, seeing how we are just practicing it right now and aren't really in a rush for time. So, according to our problem, we are dealing with Aliza Tests, which stands for Enzyme-Linked Immunosorbent Assay. These plate-based assays are designed for detecting different substances, from peptides to antibodies. These are used commonly in the lab and are familiar to those studying biomedical laboratory science. The introduction tells us that they help us identify whether a patient has contracted HIV, and that the way Aliza tests do this is by checking for proteins that the body makes in response to HIV, specifically antibodies. Blood samples from the patients are added to cassettes that contain the antigens for HIV. The patient's blood samples are then put into the assay. If the blood contains antibodies to HIV, it will bind with the antigen in the cassette and cause its contents to change color. Else, there will be no color change. These results are further alluded to in the question, which states that if the ELISA indicates the presence of HIV in the sample, the results are said to be positive, while an absence of indication for HIV is a negative result. However, there are limitations to this process, as described in the question, which states that variability in antibody levels amongst patients cause a lack of a correct result, leading to what is known as false positives or false negatives, which means that the test result incorrectly indicated the condition, in this case HIV, is present or absent respectively. Now, we don't need to know all this background about Aliza tests to actually solve this problem. But this question shows the wide range of applications for statistics in the real world, especially in laboratory science. So the next time you do your practice problem on your own, it might be helpful to actually slow down and read the surrounding context of the question, so that you learn more about how statistics is used in the everyday world to solve everyday problems. On to the actual question. Here we are given context to the specific problem given to us. Notably, that for two different 500 blood samples, with one group containing HIV and the other not, there were 489 positives and 11 negatives for the HIV blood group, and 37 positives and 463 negatives for the non-HIV blood group. Since we now know about false positives and false negatives, we can see that the negatives for the HIV-containing blood samples are false negatives, since we know these samples do have HIV, while the positives in the blood samples that do not contain HIV are false positives, because these are known not to contain HIV. This also makes sense given that these values of 11 and 37 are considerably smaller than their counterparts. Now Part A asks us to estimate the probability that the ELISA test will be positive for the blood samples that do not contain HIV. For this part, we can just refer to the chart we made and see that out of the 500 total blood samples from the non-HIV sample, 37 were positive, or are false positives, which has a 0.074 probability of occurring once we divide these two numbers. In Part B, we again have to refer to our chart, as it asks us, out of the blood samples that provided positive ELISA results, which actually contained the HIV. Since we want all positive results, this total is going to include our false positives as well, leading to a total of 526 samples. However, we then want to know how many of these 526 samples actually contain HIV, which then excludes the false positives, which is 489 out of 526, which equals 0.9297. Part C is a lot more wordier, but we won't let the phrasing of this question trip us up. We are told that for every positive ELISA result, 2 more ELISAs are performed, regardless if they are false positives or not. If out of these 2 additional tests, at least one is positive, another more expensive ELISA is done. Now this part states that repeated ELIZAs are assumed to be independent, and this is just a hint for us to know that we can use the multiplication rule for probability, since each event, which is a result of the assays, are independent. The question is asking us to find the probability that the expensive assay is even undergone, in the case that the sample does not contain HIV. This entire scenario can be written through a probability statement, where the probability that the first ELIZA is positive and not both the second and third are negative. So what does this statement mean? Well, we know that the first ELIZA has to be positive, and the probability of that occurring is the same probability we had gotten from part A of this question, where the probability that an ELIZA is positive for a sample that does not have HIV, essentially a false positive, is 0.074. Given that the first ELIZA is positive, 2 more ELIZAs must be done as well, which leads to our AND. For probability, we multiply when using AND, so we must multiply 0.074 by the expressions we find next. Now onto the tricky part. We said that at least one of these 2 additional ELIZAs had to be positive, so either the second or the third ELIZA had to be positive. This negation sign negates both the terms both and negative, leading to the phrase second or third is positive. Now the reason we have this negation is to make our math a little more easier. Starting from the inside, we know that the probability of an ELIZA being negative for a sample that does not contain HIV is 1 minus the 0.074 probability from part A, which is 0.926. Since we want the second and the third ELIZA to be negative, according to our probability statements, we multiply 0.926 by itself. Now again, this negation tells us to do the opposite of whatever the statement is telling, which we can incorporate into our actual statement by subtracting 1 from the product of 0.926 multiplied by itself. This leads to a more simplified numerical probability statement as 0.074 times 1 minus 0.926 squared, giving us a final probability of 0.0105. I hope this video helped you to solve this practice FRQ, as well as to see the applications of statistics concepts in other fields in everyday life.